Hello, welcome back. All right, we've been talking about the continuity equation. And as I've told you, it's a lot like chewing gum. All right, so here it's written out for you. du dx plus the dv dy plus dw dz equals 0. All right, so we're going to be looking at how we can use the continuity equation to understand this example about the North Atlantic Gyre. All right, so first thing we see here is it says the North Equatorial Current, the southern current in the North Atlantic Gyre, moves from east to west. So first thing I want to do is get a reminder of what that looks like. All right, so here is our North Atlantic Gyre, and down here, this is the current we're talking about in this example, is the North Equatorial Current, and we see that it moves from east to west right here. And then over here, of course, we have our Gulf Stream. And so this is the part of the gyre that we're going to be talking about in this example. All right. So the next thing I want to look at here. All right, so we assume the North Equatorial Current moves only in the east-west direction. At 70 kilometers from Florida, the current is moving at 0.119 meters per second, or 11.9 centimeters per second, if you want to think of it that way. At the coast, at 0 meters, we're defining this as our origin right at the coast. So when it hits the coast, we're saying that's our 0 point. The current can no longer move west, so it slows to rest. So it comes all the way down to 0 meters per second at that point. What is the change in u with respect to x, du dx, in this region? All right, so let's get started trying to think about this. So the first thing that we're trying to figure out, let me go ahead and rewrite our continuity equation right here. All right, so our continuity equation is du dx plus dv dy plus dw dz equals 0. All right, so that's our continuity equation. And the first thing that we're going to be looking at, the first piece of that we're going to look at right here, is we're trying to figure out what's going on with du dx. All right, so let's try to figure out du dx. So we're asked about du dx. Okay, so du dx, that is telling us that it's the change in u in x. So what I want to find out, I can rewrite this as the change in u over the change in x. All right, so that's the same thing as saying, in this case, I'm going to say that's my u final minus my u initial over my x final minus my x initial. All right, so if I go back to my problem, I see that my u final is right here. That's where it comes to rest at 0 meters per second. So u final is 0 meters per second. That's my final velocity when it hits the coast, 0. Okay, now my u initial was 0.119 meters per second, but that was the magnitude. So we have to remember that this current was moving from east to west. So it's going in the west direction. So the west direction is the negative x direction. So I'm going to do this as minus a negative 0.119 meters per second. All right. Now on the bottom of my fraction here, I have x final, and we said that x final is when it hits the coast. So that's 0 meters. That's right here, our 0 meters. So that'll be 0 meters. And our x initial was when it was out there near Florida at 70 kilometers. I'm going to go ahead and put that in terms of meters because our velocity I put in meters per second. All right. So we've got our ratio written out here. The first thing I want to point out is that if we look at this in the top, we're going to have minus a negative. So the change in u, in this case, will be positive. And the change in x down here, we have 0 minus a number. That'll be a negative. So a positive over a negative will give us an overall negative. Okay, so let's think about what that means first. Let's go think about what that means first. And all right. All right, so if we have our box, remember that we have our box right here. So what we're saying is that inside our box, the volume doesn't change. That's what the continuity equation tells us. That inside our box, our continuity, our total volume doesn't change because we assume that the water is incompressible. So we're not concerned about conserving the mass because if the water is incompressible, then we can just look at conserving the volume, and that'll be the same idea. That'll give us the same thing if the water is incompressible. So over here, what we're saying is that if du dx, so our du dx is a negative, so that means that the du coming in right here, if we're looking at it in the direction that they have it here, ours is going the other way, that's okay. The du coming in right here, if it's negative, that means that this is bigger, this arrow right here is bigger, and this arrow right here is smaller, right? Because it's bigger and then it's slowing down. All right, so that means that there is more coming into the box than leaving the box. So the only way to maintain the volume in this box is if in one of the other directions, in the Y or the Z direction, there is more going out of the box than is coming into the box. All right, so let's see what we actually get. You go ahead and turn off the video for a second, pause the video for a second, and see what you get. So, all right, du dx. If I put that into my calculator, I'm going to have positive 0.119 meters per second over a negative 70,000 meters, and I end up with negative 1.70 times 10 to the minus 6th. And that, see, we have meters per second over meters. The meters cancel, so the units of this will be per seconds. All right, so let's think about this negative. I just talked about this. So right here, we have a negative. All right, so this is telling us that in our case, if we look at what's going on with our current, it's starting over here somewhere, and it's going 0.119 meters per second. And then it's slowing down as it's getting near the coast. It's getting slower and slower as it's getting near the coast. And if I draw my box right here, I can draw my box anywhere I want to, so let's just go ahead and draw our box. right here. All right. So I've got my box right here. And what I see is that there's more water coming on this side than is going out on that side. So if I have a negative value for du dx, if I have a negative value, that tells me this means that the water is piling up in the box. All right. So we've answered the first part of our question. Let's come back to our question here. All right, let's come back to our question. And we've answered that first part. The first part asks us, what is du dx in this region? So here's our du dx. It is negative 1.7 times 10 to the minus 6 per seconds. And we know that because it's negative, that's telling us that water is piling up in the box. All right, the next part says, assume that there is no change in vertical velocity. That means that dw dz equals 0, and that the ocean is continuous. All right, so this assumption means that right here for dw dz right here, this is 0. So I'm going to set dw dz equal to 0. All right. So what I want to figure out now is, what is the change in v with respect to y, dv dy in this region? Well, if I set this equal to 0, and I know what du dx is, I can just solve for dv dy. So if I rewrite this down here, so if I rewrite this right here, I see that du dx plus dv dy equals 0. And so dv dy, if I just subtract du dx from both sides of the equation, dv dy equals negative du dx. So since du dx is negative 1.7 times 10 to the minus 6, we end up with a positive 1.7 times 10 to the minus 6th per seconds. All right, let's think about what this means. This means we've got a positive this time. So this time this is positive. All right, so in this case, we're saying that in the y direction, which remember is going this way, that we're starting really small and then increasing. If we have it getting increasing, we're saying if that's what this is telling us, if dv dy is positive, then the change of v in y is increasing in the y direction, in the positive y direction. All right. So that makes sense. That makes sense because what we were saying was that what we were saying was that if there is water that is coming and piling up in our box, then somewhere else it has to be rushing out of our box. So the fact that this is positive tells us when our partial derivative is positive, that tells us that water is rushing out of our box. All right, so now let's go ahead. We've answered the second question too. We figured out what is the change in y with respect, change in v with respect to y, dv dy in this region. And we saw that dv dy is positive 1.7 times 10 to the minus 6 per seconds. All right, let's look at the next part of the question. Assuming that the north-south current, the Gulf Stream, starts at rest, so v equals 0.00 meters per second, and all the water flows to the north. What is the speed of the Gulf Stream when it passes Cape Hatteras, 1,500 kilometers to the north? All right, so in order to answer this, let's go ahead and take what we have here, what we know for our dv dy equals 1.7 times 10 to the minus 6 per second. I'm going to write that on a new page. All right, so we're going to start with the fact that we know that dv dy equals our positive 1.7 times 10 to the minus 6th per seconds. And what I want to figure out is what happens to v when it has moved a certain y. So I have dv dy, and what I want to know is what is v in terms of y. In order to find that, I'm going to do, first step is separation of variables. So I basically am going to take this dy and put it on the other side of the equation, or you can think of it as multiplying both sides of the equation by dy. So right here, I have my dv is equal to this constant 1.7 times 10 to the minus 6th per seconds times dy. And now I have dv on this side, dy on that side. I want to get v, so I'm going to integrate. So I'd integrate this side of the equation, and I integrate this side of the equation. Now we're going to be going from the same point to the same point. So we're integrating from the point where the velocity is 0 meters per second, right at the coast. And we're going up to some velocity, let's call it v1. And we're starting that point at the coast, we said right here. We defined that as our 0 meter point, so that's our 0 meters here. And we're going up to 1,500 kilometers. So that's what we're doing with y. We're increasing it 1,500 kilometers to the north. All right, so if I integrate dv, I just get v. Nice. And that is defined from 0 to v1. And on this side of the equation, I can pull my constant out in front of my integral sign. Integrating dy, I just get y. So I have my 1.7 times 10 to the minus 6th per seconds times y, where y is going to go from 0 to 1,500 kilometers. All right, so this tells me I do b minus a, so I have v1 minus 0 on this side of my equation is equal to my constant 1.7 times 10 to the minus 6th per seconds times my b minus a on this side, my 1,500, I'll go ahead and put the 3 zeros there, meters minus 0 meters. All right, so I end up, go ahead and do it yourselves with your calculator. V1 equals, if I put this in my calculator, I end up with 2.55 meters per second. and that's positive, and the positive V direction we know is to the north. And that's what we expect. If we look back here at our box, we saw that our velocity was speeding out of our box to the north. And if we think back on our gyre, we know that the water piles up. The water piles up along the all over here near Florida from the North Equatorial Current, and then that water moves up in the Gulf Stream to the north. All right, so this is our example of continuity and how it applies to the North Atlantic Gyre.